Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in Finland. I study cosmology. So that means that I study the universe, the contents of the universe, how everything revolves, how everything interacts, basically all of the cool things happening inside the universe. And I love chatting about science, about cosmology, about what I do with everyone. So that's why Cup of Cosmology is here, so that anyone in the world can tune in and ask all of your questions about science, about space, about cosmology, all of the cool things. Now, wherever you're watching from, hello and welcome. If you're a return viewer, welcome back. Always nice to see the regulars. If you're new, welcome. If it's your first time here, please do click the subscribe button on whichever platform you're watching on, and like, leave a comment, do all the usual YouTube things to boost visibility. I always forget to ask people this. So hello, David Dunn in first and David Howden, the two regular Davids. Great to see you both. Thank you for being here. Holodeck safety protocols engaged, awesome. So we're already getting started. So indeed, today's topic is holography. Now, holography is a great topic and one that I will absolutely not be able to talk about by myself. So I do have a guest joining me today, and I'm just going to bring Oscar up on the stream. Hello and welcome to Cup of Cosmology.
Hello, Diana. Thank you. Great to be here.
It's great to have you here. So do you want to introduce yourself to everyone?
Sure. So my name is Oscar Henriksen. I'm a postdoc in theoretical physics at the same place as Diana here in Helsinki at the University of Helsinki. I don't know if you want me to talk about myself. I'm from Finland originally. I did my studies in Uppsala in Sweden, and then I went to the US for my PhD. Then before I returned sort of home here. And I do research on holography or holographic duality, as I guess we'll get into more soon.
So it's a great topic, and we're definitely going to try to discuss all of that. So let me just say hello to everyone here in the comments, all of the regulars. Hey, James, Paul, great to see you as always. And joining from a train. Thank you for joining, even if you're on a train. I appreciate it. Scott, nice to see you as always. Jasmine, David, all of you, great to have you here. Thank you so much for joining. So let's get started with the big question. What is holography? Take it away.
where to begin? Right. So I guess maybe the story should begin with black holes somehow.
People like black holes on this stream.
Yeah. Right. So I mean, black holes are real objects, we are fairly sure at least that exist in the universe, but. And they're, of course, sort of somewhat of a prediction of Einstein's theory of gravity, of general relativity. But physicists, so theoretical physicists, at some point, I'm very bad at dates and years, but at some point, in the past, they discovered that general relativity. So if you study black holes, you notice that they sort of fulfill these laws. They follow these laws, which are sort of like the ones of thermodynamics. So black holes there are certain properties in black holes that look like kind of analogous things in thermodynamics. So, for example, entropy. You might have heard about entropy. So the second law of thermodynamics says that entropy always increases. Well, for black holes, there's a similar thing about the area of the black hole. So area of black holes always increase.
Maybe we can just comment there on what entropy is, just in case not everyone has heard of entropy. So entropy is basically the chaos of a system, which was great when I started studying physics, because then I could just say, entropy increases. My room is not messy because I'm a messy person. My room is messy because of entropy.
Right.
I'm not impressed by that answer. But yeah.
It's natural, yeah.
And entropy, it's just the amount of chaos in the universe. So yeah, within the universe, everything tends to be maximum entropy, so maximum chaos. And you were just saying within a black hole instead where it tends to have a bigger area.
Right. So I mean, at first, at least my understanding is that at first these laws, the fact that they look like thermodynamics was kind of a cute coincidence. Like I'm not sure if anyone really thought that it was directly related to thermodynamics at first, but this sort of changed. I guess one important thing is then when Stephen Hawking of fame from various things showed that black holes should radiate, so that black holes effectively have some kind of temperature and that they actually radiate. And this kind of fully connected them to thermodynamics in some sense. And I guess if not before, then that's when people started really taking this black hole thermodynamics seriously. Okay, so if we do that, then okay, so the area, like I said, the area seems to correspond to the entropy in that case. But that's kind of weird, because if you think about entropy, so entropy, like you said, it's kind of like a measure of disorder or chaos. And typically you expect it to scale as the volume of something, right? Like if you have your room, for example, Diana's room here, your messy room, the maximal disorder should somehow be proportional to the volume of the room. That's kind of what one would expect, at least. Like the more volume there is in your room, the more the more messy it can be, the more disorder you can fit in there. But yeah, so it seems like for black holes that's not the case. So it seems like for black holes the area, the sort of enclosing area, is what sets the maximum disorder. And this, okay, so this is now starting to get us into holography, right? So I should say maybe now that I mean, there is also optical holograms, which are, Star Wars, when the
holodeck.
Holodeck. Oh yeah, holodeck, of course, yeah. So this, what I'm talking about, has not much or if anything to do with that. The only thing it has to do with, or the only similarity is this kind of how do you say, difference in dimensions, right? So optical holograms, you store kind of a 3D picture on a 2D surface, and the idea that people had is that, okay, gravity seems to be somehow holographic. Black holes seem to be somehow holographic, because all the information, somehow all the information about the black hole is stored somehow in the area, on the event horizon. So maybe you've talked a lot about black holes already, but the event horizon is sort of, well, the boundary, let's say, roughly.
The point of no return. Anything that crosses the event horizon will fall into a black hole. Before the event horizon, you could still escape. So right, this basically means that any mass or anything that falls into the black hole, we often ask the question of what happens to the information that is contained. And with the holographic idea, what we're saying is that all of this information basically stays on the surface of the black hole.
Exactly. And there's this idea, there are these various arguments for why, so this is sort of telling us that black holes are holographic, but then there's sort of these extending arguments that say that, okay, if that's true, then kind of everything, as soon as you have a theory involving gravity, things should be holographic in some way, because, if you start out with some volume and you try to fit as much disorder in as possible, and that basically means you have to put things in there, right? If you want to increase the amount of entropy in a certain volume, at some point collapse into a black hole, and then the black hole, for black holes, the maximum entropy is proportional to the area. So then this is somehow taken to be, or argued to be, a that sort of the maximal entropy, the maximum entropy in a certain space is proportional to the area enclosing that space. So that's kind of this holographic idea. Yeah.
Yeah, it's a lot to take in. It's a big concept, and it will be important for the rest of the things we're going to discuss today. So if you have any questions about this, now's the time to ask. Before we move on too much from black holes, we've mentioned the word entropy and the word information. So Paul here is asking, is entropy related to information? Are they proportional? Are they inversely proportional? What is the connection between entropy and information?
Right. Yeah, I mean, there is a connection. Yeah, that's a good question. Yeah, I mean, basically, entropy is somehow a measure of how our lack of information, I guess. Right. So they are somehow inversely proportional in that sense. Yeah. That's right.
Yeah, I think the slight issue here is that entropy is a clearly defined concept in thermodynamics. We know exactly what it is. It's the degree of chaos. Whereas information we sometimes use to mean the energy contained or the knowledge contained. So it's quite hard to write it down in a mathematical expression where you can relate the two.
Yeah, I mean, there is sort of this whole kind of branch of mathematics and called information theory, and which is also much used in physics. And you can define entropy information in a sort of rigorous way, and then they also in fact talk about something called entropy in that area, in that field, which is basically the same thing as what we physicists mean, what we call when we talk about entropy.
That's one of those times where we say it can be defined, but we're not going to give the exact definition. It can be by somebody else. Scott is asking if that's a tea kettle we can hear whistling in the background.
Oh, from me? I don't think so.
No, I don't think we already have our tea, so it shouldn't be a tea kettle. Going back to your question by Jasmine here, if the black hole is radiating mass in the form of Hawking radiation, how is its area increasing?
Good. Yeah, that's a confusing thing. One should add some things to that. So the statement that the area always increases, that's a prediction of classical general relativity. So by classical I mean not quantum. So no quantum mechanics. So if you just take general relativity as a theory, then it predicts that the area should always increase. However, then what Hawking did was to add to the mix quantum mechanics, or what's called quantum field theory, more if you want to be more specific. And he showed that in that case, indeed, black holes radiate, and then they lose mass, and then indeed their area can decrease. But so then you might ask, okay, what happens to the second law of thermodynamics, or black hole thermodynamics? Well, the statement then is that the total entropy of black hole plus radiation still increases.
I think there's an important point to mention there, that when we say the entropy always increases, it means in a closed system.
Yes.
A black hole is not directly a closed system. Once it's radiating energy, it is now interacting with something else. So then in order to not violate the entropy increasing in second law of thermodynamics, we have to take into consideration that it's actually no longer a closed system. So we can have both. A black hole can be slightly decreasing and losing mass because of Hawking evaporation, but it can also be growing as it has things falling in towards it. Sticking on the topic of information and entropy, does information have mass? Does entropy only refer to mass? Tough questions already.
Yeah, let's see. Does information have mass? I mean, not necessarily. It depends a bit on what you define as information. I mean, you can, again, like going back to this, if you want to go to this mathematical field of information theory, then you can, if you give me a text, for example, a text in, written in English, for example, there is a kind of definition of what the information of that text is. So any sort of message in that sense has information. So information doesn't have to be directly related to mass. Of course, you always need. You can argue, I guess, that you always need some mass to kind of store the information on, perhaps. But
I guess then we could argue that we have an example of photon, which is a particle of light, which is massless. And a photon carries energy and therefore also contains some amount of information. So I would say that you do not need mass to have information.
Very good, yeah. So maybe energy, though.
Yes, you need some form of energy, I would say, but not necessarily mass. But yeah, it gets fun when we define information.
Mm-hmm.
So putting it all together again, just to recap, and again, do ask questions if you have any, because this is a complicated topic. This is why I've got an expert with me today, so I don't have to explain it myself. So what we're saying here is that all of the information of a black hole is contained on the surface of a black hole. And because a lot of things in the universe behave basically similar to black holes in the sense that they're objects with gravity, then we can ask the question of, does this logic apply to other things? And does this holographic principle idea of everything contained on the surface apply to anything else in the universe? So I think, would you agree that that's a summary of where we were?
Yeah, sounds very good. I'm happy.
Okay, so now that we're here, why is this important? Why do we care that all of the information is contained on the surface? What does this tell us?
Right. Well, the idea is that this is somehow then something deep about gravity, or maybe I should add here that this is something deep about quantum gravity, because okay, so gravity, in the sense of general relativity, we understand pretty well. We think we do, at least, but there is things we don't understand, and one of these big open questions has to do with quantum gravity, like the unifying or somehow finding a theory that encapsulates both gravity and the laws of quantum mechanics. So
why do we want to put quantum world and gravity together?
Well, why not?
I like that answer.
Yeah, why not? I mean, it's sort of, well, for one thing, unification has, of course, been kind of a theme in theoretical physics for the last, I don't know how long. And it's always nice to unify things and have laws for everything. But I would also say that on a even more kind of fundamental level, I mean, we know that gravity is it's a thing. It exists. It's a part of our universe, part of our world. We also know that quantum mechanics is a thing. It's very, very successful, extremely successful theory. And it would be nice to know that they work together, that they fit together. And I mean, they must, right? Because we are here. This universe is here. So unless
they must talk somehow.
Yeah, exactly. So unless the universe is somehow logically inconsistent, which could happen, I guess. But unless that is the case, then they should somehow fit together, and it's fun to see if we can figure out why or how they fit together.
Another way of thinking about why we want to put everything together is we know there are four forces, or at least we found four forces so far in the universe: the gravitational one, the electromagnetic one, the strong nuclear force, and the weak nuclear force. And we know that if you go backwards in time in the universe, you go to higher energies. And when we go to higher energies, these forces were actually united. So we know at some point the electromagnetic force and the weak force were combined into electroweak. Pretty sure strong force was also combined in there at some point. And all of these are forces that we understand on the quantum level. So if we want to put gravity in some kind of theory of everything unifying all the forces, we need to figure out how gravity behaves on a quantum level. For this, we need quantum gravity.
Yeah, and I mean, I guess since this is a cosmology stream, another motivation is also the kind of the Big Bang, or the original singularity, right? Like right now our best theories. I mean, the theory of Big Bang and so on, which you probably heard Diana mention many times. They predict that at some point, if you rewind time far enough, you often end up in a singularity, typically end up in a singularity, and where the curvature of space and time becomes infinite, right? And this is something that we would like to kind of understand, and basically the fact that the curvature is infinite, then that kind of is general relativity telling us that it doesn't know what happens anymore, right? Like infinite curvature. It just doesn't make sense. It's a singularity.
It's just weird things. We do need quantum gravity to understand the first seconds of the universe.
Right.
We have two very fun questions here. I'm going to read David's first. Does Gödel's theorem mean any theory of the universe must be either incomplete or inconsistent? And this feels like a super tough question that I absolutely do not want to answer. Do you want to give that one a go?
That is tough. Gödel's theorem. Let's see. Yeah. So that's. I mean, I can't even properly phrase that theorem, but I guess it's somehow the idea that there are always things you cannot prove or disprove.
I think so. It's somewhere at the back of my brain.
Yeah.
Like, I'm happy to skip that question and save that for next week.
Yeah, I mean, in principle, that could apply, right? I don't think it implies that the universe must be incomplete or inconsistent, but it is true that there might be things that we can never prove or disprove. I mean, this is mathematically now. Of course, in reality, we hope that we can do experiments. I mean, that's the ideally, at least, if we can actually do experiments, and then we can check if things work or not. But it's true that there might be things that are impossible to prove or disprove. Yeah, that's right.
I think that's what keeps our job fun, right? The day we know everything, the day we prove everything, physics becomes boring. And going slightly off topic, because we got into the forces and gravity, we have two related questions here of, is gravity actually even a force, and could it be a fictitious force? Because we threw it together with the other three forces very happily, and now people are questioning that.
Yeah, this is a good question. This is really hard because the terminology is somehow, well, I mean, so like what does one define as a force? What is a force? Like, in Newtonian mechanics, a force is kind of, well, it's whatever creates acceleration, I guess. But yeah, I mean, there is this idea that gravity is in some ways kind of like a fictitious force. And okay, now we have to introduce what a fictitious force is. So, for example, if you are, I don't know, is this going too far off topic now?
No, let's go. It seems like a fun question.
So, I mean, there's this famous Einstein's elevator thought experiment. Have you heard about? Do you know this one, Diana?
I know where you're going.
Yeah. This thing, like if you imagine you're standing in a box, let's say an elevator with no windows, and it's standing on Earth, so you're experiencing gravity. So the elevator is just standing still at the moment. So you're experiencing gravity, and everything is falling down with some force, some acceleration. But then now, if you took this elevator and put it far out in outer space, where let's assume there's no gravity, but now instead some kind of spaceship is pulling the elevator upward at the same acceleration, at this 9.8 meters per second squared, the same acceleration that things fall with here on Earth, on this Earth's surface, then you couldn't tell the difference, right? And that's the second case there in out in far in space. That's kind of a fictitious force. Like from your point of view, it feels like things are there's some force pushing you down towards the floor, but there's not really a force, right? Because it's just someone's pulling the elevator up, accelerating the elevator upward. So that's I guess one example of a fictitious force. And indeed, this very example tells you, right, that gravity kind of looks like a fictitious force in that sense, because you can't tell the difference sitting in this dark, sad elevator.
Yeah, so I like that people basically want us to define gravity. We're still trying to figure out how to do that. So we can consider it a force for some discussions, and for other discussions we'll say it's a curvature of space-time, and both of those are true. Depending in the context, we'll use one or the other, because we're still trying to figure out what gravity is and how we actually deal with gravity. Which brings us back to what we were saying, and we have the question here by James of, when we're saying the information is on the surface, are you referring to like the event horizon? Just to clarify, that when we say the information of the black hole, it's on the event horizon of the black hole.
Yes, yeah, that's a good question. Yeah, indeed, it's the area of the event horizon, indeed. Yep.
Right. So before
I just see David Dunn here mention principle of equivalence, and that's exactly this Einstein's elevator thought experiment is kind of an illustration of this principle of equivalence, indeed. Yep.
Let me just mention there that David Dunn is an astronomy professor and has his own show over on Twitch, the Astronomy Show, every Sunday, I believe a couple of hours after this show, actually. So do make sure you follow David Dunn on Twitch as well for more space stuff in your life. David's also a great broadcaster that we have around here. So we were talking about quantum gravity. Just to bring it back, how is the idea of quantum gravity, or uniting gravity with the quantum world? How do we connect this to holography again?
Yeah, so I think maybe at this point, string theory should enter somehow. So
I have been asked about string theory many times, so go ahead.
Yeah, we haven't mentioned that so far. So this idea about holography, gravity being holographic, was kind of around for a while, and I think it was some people. Let's see. Tuft, Susskind, maybe some other famous theoretical physicists that had this idea that there should be some holographic principle of gravity. But this remained, I would say, fairly vague until the end of the 90s, 1997, I think, when a physicist called Juan Maldacena came up with something called the ADS-CFT correspondence. Okay, and this is a concrete realization of the holographic principle. So he was able to show or argue that there are two theories. Okay, so there are two different theories, and one of them has gravity. One of them is gravitational. The other one is not. But he was able to argue that these are equivalent. These should be equivalent. Okay, and we can go, if we feel like it, we can go more into the argument there. But that's the argument. And the interesting thing then, of course, is that this correspondence is holographic in the sense that the theory with gravity lives in more dimensions than the theory without gravity. Okay, so roughly speaking, at least, if the gravity theory has 3 + 1 dimensions, so 3 spatial dimensions and 1 time dimension, like our visible universe, then this other theory has 1 dimension less, so 2 + 1 dimensions. But they're still supposed to be equivalent, right? So any kind of calculation I can do in this theory, I can translate into this other theory, and vice versa.
So if I can just summarize this, just because we are throwing up a lot of new concepts here.
Yes.
So the cool thing about the holographic idea in black holes is you take all of the black hole, which should be 3-dimensional, and all of its information is encoded in this 2-dimensional surface. And now the idea is, what if we could do this to actual theories of physics that are useful to us? If we could relate, in this case, a higher dimensional one to a lower dimensional one, this is very useful because you can do calculations in one and they're equivalent to the other. So you can solve everything in one less dimension and then map it back to the original one.
Mm-hmm.
So you mentioned that the concrete example of this holographic theory is ADS-CFT.
Yes.
Maybe we should briefly mention what ADS is and what CFT is, and we still need to connect this to string theory.
Yeah. So actually, I kind of wish I hadn't used the name ADS-CFT now that you say, because it's kind of an ugly, annoying name. But okay, yeah. So there it's 2 abbreviations, right? So it's ADS and then CFT. So ADS refers to the gravitational theory, and it stands for anti-de Sitter. And it's a specific, it's a space-time with negative curvature. Okay, so this is
it's basically a closed, curved space, right?
Yeah, it's not necessarily closed, but it's sort of like I mean, the easier to visualize thing in 2 dimensions is a saddle point.
Right, it's the oval one. Yes, the other one.
Yeah,
like a Pringle crisp.
Oh yeah, that's a good one. Yeah. So it's something with negative curvature. Yeah, I mean, so people might have heard of, more likely to have heard of de Sitter space without the anti. So just de Sitter space. So that's actually that's a universe with constant positive curvature, and that's actually what our universe might end up in the far future, right? If this dark energy keeps accelerating the expansion and so on.
Yeah, so we're not completely sure on the shape of the universe. Currently, we think it's flat, but in the future that could change and it could end up positively curved. Mm-hmm. But yeah, ADS is basically the gravitational theory that we're using in this case. Yeah. I think we probably don't want to go too much more into ADS unless there are more questions on that, but we have the CFT part as well.
Yes, okay, so CFT, CFT is a special type of QFT, which is so CFT stands for conformal field theory, which is a special type of quantum field theory. So I mentioned quantum mechanics earlier, and I mentioned quantum field theory very briefly, which is the quantum theory of fields. Okay, so this is basically the standard model, for example, that people might have heard of, which is our best theory of particle physics, fundamental particles and fundamental interactions. That's one type of quantum field theory, and the CFT is sort of a specific subclass, I guess, of quantum field theories. Yeah,
So
maybe I don't know if we should go too far into that.
I was just going to say maybe we should specify what a field is, because that's a word that we throw around often and without thinking about it sometimes. You can imagine a field as something that has a specific value everywhere. So if I ask you the temperature in Helsinki, you'll probably take a thermometer somewhere and say, okay, it's 19 degrees, which it currently is 19 degrees, at least according to my kitchen thermometer. But this is in one point. If you take this measurement in every different point of the room, for example, if you're close to the oven or if you're close to a fan, you might get a different temperature. So in every point that you measure, you can get a different value. And usually when you quote a value, you're quoting the average over some specific area. So when we're talking about fields, we're basically saying something that has a value everywhere where you could possibly measure it. Do you agree with that definition?
Very good. Yeah, I agree.
Yeah, so quantum field theory is the idea that all of the particles and the forces can be expressed as fields, which have a specific value everywhere in the universe. Mm-hmm. And CFT is a specific version of quantum field theory.
Yeah,
and thanks to the holographic principle, we can relate this gravitational theory with this conformal field theory.
Yes.
So you mentioned that we should bring in string theory. So how is this related to string theory?
Yeah, right. So string theory is so we talked earlier about trying to unify gravity with quantum mechanics. That is basically what string theory is supposed to do. Okay, so string theory is indeed it's a theory of quantum gravity. So there's a lot of kind of confusion about this. I mean, it's not string theory is not proven or anything near proven. So it's just it's one possibility, one possible theory of quantum gravity. But it seems to work pretty well, and it has given many interesting theoretical results, and indeed this holographic duality, or this ADS-CFT correspondence, as it's sometimes called, that's one of them. Yeah, I see someone commented that my clock has stopped, and that's indeed the case. Yeah, it's been out of batteries for 2 days, but I've
you're close to an event horizon.
Yes, it fits very well. Yeah. Yeah. So string theory, right? So string theory tries to unify quantum mechanics and gravity, and it's sort of natural in a way that it should have. So it should have something to say about the holographic principle if it is indeed a thing, and lo and behold, it does. So this physicist Juan Malacena showed that at least for certain gravitational theories, we can explicitly tell you the holographic dual. So what the lower dimensional theory is exactly.
Then this is interesting because it makes it easier to do calculations because we can skip one dimension.
Yeah. So I mean, there are several sort of ways to use this holographic duality once you have it in hand. But yeah, exactly. One neat thing is that you can do kind of calculations in the gravity theory, and that gives you information about this dual quantum field theory, or you can do calculations in the quantum field theory, and that gives you information about the gravity theory. So you can kind of use them in some kind of complementary way here. That the questions that are hard on one side might be easy on the other side, and you can use that to your advantage quite a lot. And indeed, that's basically my research is using that, trying to use that in some good ways.
So before we get into that, because I have a lot of follow-up questions, there's a question by James here. Is the info that's not entering the black hole, is it because it's rotating on the event horizon, or is there a unique force, horology, that keeps it from falling in? I have not heard of horology before. So basically, is there something preventing the information from entering the black hole, or why does it stay on the surface?
Yeah, that's a good question. I don't think anyone, or well, no one knows the exact mechanism that is at work here. Of course, we have never been inside an event horizon, and we never will be. Or well, if we go in, we will not come out.
And we'll not be able to send any information back either.
We might come out as radiation, but that's not very useful. So it's hard to say. So there are various proposals for what actually happens, and none of them is completely successful. But indeed, there are some physicists that have proposed that basically the horizon is some kind of wall that almost like a physical wall that comes against you when you fall into the event or fall into the black hole, and that basically everything is kind of stopped in some sense there. But I would say that this is on the level of very controversial and speculative, extremely speculative. So it's
we should mention as well. Yeah, not everyone believes that all of the information is contained on the surface of a black hole, because it's not something we've been able to prove in any way. Mm-hmm. So it is useful to build up this whole as a proxy to build up this holographic idea, but it's not necessarily true in black holes. Mm-hmm. We have a question here, which I like a lot. How much time dilation does a black hole experience relative to Earth's reference frame? This is very interesting, and it basically depends on the mass of the black hole and where you are in relation to the black hole and who you're comparing yourself to. One very nice example we can actually point to is Miller's planet in Interstellar, where there's a planet orbiting a black hole, and anybody on that planet will experience time dramatically different to anyone back on the spaceship. And they actually did a proper calculation of time dilation. So in answer to your question, it very much depends on the mass of the black hole. The bigger the black hole, the more time dilation you'll experience, but it also depends on how close you are to the black hole. And then you can calculate your time dilation. Mm-hmm. Yeah. Question from Jasmine here. I thought the big advantage of holography was moving from a strong to weakly coupled theory, not the lower dimensions. I do believe Jasmine is a physicist. If it is the Jasmine, I think it is, which is why we're getting great questions. We're getting great questions from everyone today. Yeah. So do you want to tackle that about strong to weakly coupled theory?
Yeah. So that is correct indeed. That is probably the more accurate way to say it indeed. So this duality, this holographic duality, it maps the parameters of these two models, to these two theories, to one another. And indeed, when the gravitational theory is strongly interacting or strongly coupled, so basically it's sort of heavy quantumness going around, I guess. Let's see, something like that. Then the quantum field theory is weakly coupled and easy to work with, and vice versa. So when the quantum field theory is strongly coupled, when this dual theory is strongly coupled, then the gravitational theory is weakly coupled, which in that case just means it reduces to kind of simple classical gravity, which is quite well understood how to do calculations. Might not be easy, but it's understood how to do it at least. So people, including myself, typically use this in the following sense, that we do calculations in this gravitational theory, in classical gravity, and then translate that to get result about the quantum field theory, which is strongly coupled. And because calculations in this quantum theory that's strongly coupled is extremely hard, and something that in general we do not understand how to do.
So this discussion about strong and weakly coupled forces just reminded me of one of the slides you showed us on Tuesday, I believe it was. Oscar gave a talk in our group, a very lovely talk, by the way. And I have the slides, and there was one slide that I was very amused by, and you just made the comment here. So I'm actually just going to bring the slide up on screen and put us to the side. Okay.
Yes.
Because you have this comment here about strong coupling, life is hard unless you do holography.
Yes.
And the idea here that you have ADS-CFT. So I was very amused by this. And do you want to just explain, I think you were about to get into it anyway, but why is strong coupling why does strong coupling make your life hard, and how does holography make it easier?
Yeah, so I mean, the typical way that we learn how to do quantum field theory and, well, many other things in physics in general is something called perturbation theory. And perturbation theory basically means that we start with something we understand well and that we can completely solve theoretically. We can solve the equations, and then we perturb. We move away from that a little bit, just a little bit. So we still understand what we're doing. We can kind of compute corrections to that. So in quantum field theory, the thing we completely understand that's really easy is free field theory. So that means that there is no interactions. If you have a photon, for example, it just goes and does its own thing. It doesn't see any other particles, doesn't care about any other particles. So it's completely free. All the particles are free, not interacting. And that you can calculate, and you can understand everything. And then you can do perturbation theory, which kind of slowly adds some small interactions. The photon might be absorbed by an electron, emitted once. Some tiny little corrections to that. And this we can do. We understand how to do, and I mean this has been extremely successful. It's not it's already a huge achievement to be able to do this, and it's led to many predictions. But it does not work when interactions are very strong, and that So in that case, we need more fancier methods maybe, and one of those is holographic duality. So there are other methods as well, like you can do computer simulations, so-called lattice simulations, and so on. But
it's kind of a way of cheating. It's like you found a cheat code. So instead of dealing with this complicated problem, you just relate it to another simpler problem, solve the simpler problem, and then hey, look, I've also solved the complicated problem thanks to this cheat code, which is holography, which always sounds magical to me. It's like, can I just throw anything at holography? Why not? But of course, you need it. You need this duality. You need this correspondence.
Right. Yeah.
We have a good question from Paul here, because we mentioned the ADS example where we had the curvature of space-time. So Paul is asking here if the holographic theory is useful only in positive or negatively curved space-times. Can we use it in both of those? And I'll add the follow-up question of, can we also use it in flat space-time? Because we know that our local universe at least appears to be flat.
Right. So holography in holographic duality, in the way it's sort of well understood at the moment, only applies to negatively curved space. So this anti-de Sitter space. So there's various kind of technical reasons for why that is simpler to describe holographically. Well, actually, one of them, the slide you just flashed from my talk, kind of hints at that. So here you see, I mean, this is a very crude illustration, but the point here is that anti-de Sitter space is a very special space-time, because it's very nice and symmetric, but it has a boundary. It has this boundary which is kind of nice, and the technical word for it is time-like. But okay, that's a technical word. But anyway, it has this nice boundary, and where you can kind of put the CFT. So you can kind of think of this CFT or this quantum field theory as living on the boundary of this space-time. So ADS, anti-de Sitter space, is sort of well suited to this duality. It fits very nicely in. So there are proposals to extend this to positive curvature, so de Sitter space, or also flat space. But I'm not an expert here, so I probably shouldn't say too much. I think all of those attempts are in a much cruder, at a much cruder at this moment. So they're not well understood, particularly well understood at this moment. But of course, that's something we would like to have. Yeah.
So I would just like to go back to one thing here, because of course you're talking about all of the good things you can do with this holographic principle. It can simplify your calculations. It allows you to not have to deal with strongly coupled things. But you just said that, ADS is specifically for negatively curved space-time. And we know that our local universe is flat. So does this mean that what you're doing is not applicable to the actual universe? Is it just a theoretical thing? Because sometimes we talk about string theory and then need to remember that a lot of string theory is not applicable to our universe. So I just want, I know I'm putting you on the spot here with a tough question. Just want to clarify this for everyone.
Yeah, no, it's a fair question. Yeah, so certainly it depends on what you want to do, right? So certainly if you want to describe our universe, and more specifically the cosmology of our universe, it does not directly work because our universe certainly does not have constant negative curvature or a negative curvature in any way, as far as we can tell. So in that sense, it doesn't work directly, and because of that, it will be very valuable to find some kind of flat space holographic duality or positive curvature holographic duality. But that said, it's still very useful, but perhaps for some more theoretical reasons. So the holographic duality that we understand well is still useful. It tells us we can use it to kind of try to figure out a lot about quantum gravity. So it's kind of, in a way, it's the first well-defined framework where you can really do quantum gravity in a kind of broad way. So you can kind of hope to learn general lessons about quantum gravity using it, and that these general lessons might be true in also in flat space and in positive curved space and so on. So that's one way, and then the other way, which is it's very useful for kind of hopefully for the real world, is the way I use it more often, which is to kind of use it the other way around, that you do calculations in this gravity theory, which are kind of you can do in this classical limit that I mentioned earlier, and then you translate that to the quantum field theory, and you use it to learn things about quantum field theory. And quantum field theory, we know, is extremely important in the real world. Like quantum field theory describes, well, we already mentioned the Standard Model. It describes all kind of fundamental particles and the way they interact. It also can be used to describe, used in material physics, what's called condensed matter physics, to describe, metals, superconductors, and so on. It's used in nuclear physics as well. So it's basically like I would say the framework of theoretical physics in some sense. And there's still a lot about quantum field theory that we don't understand. So we can use this holographic duality to learn more about quantum field theory again and again at strong, mainly at strong interactions, because that's when things are hard in general.
Yeah, so I just wanted to clarify that, because in case someone's saying like, this is only negative curvature, this does not apply, it really does have a lot of applications.
Yeah.
There's just two comments from the audience that we should address here. Comment from Ben that we didn't actually explain what we mean by negative and positively curved spacetime. Sorry about that, that's on us, our bad. So very briefly, we know that the universe should look the same in every direction from wherever you look. This means it's homogeneous and isotropic. And this means there's only three possible topologies, which are just distributions of space-time itself that we can have. We could either have a flat universe, which is what we think we live in. We could have a three-dimensional sphere let's not use the word three-dimension. We could have kind of a sphere universe, which is what we would call a closed universe, or we could have an open universe that will look like a Pringle chip, a Pringle crisp. And with these three different let me just okay, never mind. Okay, that's better now. Okay, you put your headphones right next to the mic, and we were getting a bit of feedback, but it's clear.
Oh,
now.
I'm sorry.
It's fine. I was just looking for the mute button, but it's fine now. Sorry about that. So yeah, we have these three different possible ways a universe could be. It could either be closed, it could be open, like a Pringle crisp, or like a saddle, or it could be flat. This is really just a mathematical definition. The way we always think about it is if you draw triangles in space and you add up all the angles, depending whether you get 180, more than 180, or less than 180, you can figure out the curvature. So it's really just about how space-time is distributed. And then we have the other question, which is one for you, which we didn't actually mention. Why is this whole thing called holography? Like, where does the name come from?
Yeah, right. So this is the idea that it's similar in one sense to these optical holograms. So in optical holograms, you have a 3D. You want to have a 3D image, but you want to store it on a 2D surface. So you want to store all the information on some surface with one less dimension of lower dimensionality. And this is true also about this holographic duality, that this quantum field theory, or this CFT, lives in less dimensions than this gravitational theory. So the CFT with lower dimensionality knows everything about this, has all the information about this higher dimensional gravitational theory.
Yeah, so it's called holography because of the one thing it does share with the holodeck and the optical holograms we're used to thinking about, is that we're just encoding more dimensions in less dimensions. Just going back to this idea of open-closed universe, which I'm doing briefly because we want to move back onto holography. Our universe is going through accelerated expansion. This is compatible with a flat universe, but depending on how dark energy behaves in the future, this might change. We might lead to a closed universe or an open universe, depending on dark energy. And I'm going to leave it there because we can spend ages talking about the curvature of space-time. And I want to bring the conversation back a bit. So I've had a couple of other people from our group join us on the show. And we've been talking before here on the show about phase transitions and bubbles. So just for anyone who did not catch those episodes, in the early universe, we could have basically the universe tunnels to a lower energy. So it's in one energetic state and it goes to another one. And this can lead to bubbles of the new energetic state appearing. And this is what we call a phase transition. And these bubbles appear and then grow and expand and then eventually dominate the universe. But this is a very, very short summary of some of the other streams we've done. And these bubbles can produce gravitational waves, which is why some of us are super interested in them, because we might actually be able to find signals of these bubbles with the upcoming ELISA spacecraft. So bubbles are also connected to what you're doing with holography. So how do you use holography to study bubbles?
Right, yeah. So like you said, Diana, I gave this talk about this. So this is some recent research that me and some others in Helsinki and some other elsewhere also did together. So this is using holographic duality in this way I described just a couple of minutes ago. So these bubbles, right? They are that is something that occurs in quantum field theory, right? So quantum field theory is the thing that describes these two phases and this phase transition and how these bubbles are formed. But again, like the way people typically compute the properties of these bubbles. So, for example, their size and shape, their what temperature they start to appear at, and so on. The way you typically compute these properties is using quantum field theory and using perturbation theory. So you look at weak coupling, and there are ways to do it at strong coupling. You can do these computer simulations that I mentioned, but they can be quite
difficult.
Hard, quite difficult. Take a lot of time and computational effort and
mental
human effort. Exactly. So we figured that, why don't we try to see if we can study these bubbles and how they form using holography as well. So we kind of cooked up a way or worked to understand a way to what computation you should do in the gravity theory to extract this information of these bubbles in the quantum field theory. So again, it's a way to kind of do this same thing in quantum field theory, but at strong coupling, and using this gravitational dual to do that.
So people often joke, is a computer going to steal my job? And in this case, it's the opposite. You're stealing the job from the computer.
Yeah, that's the hope, at least.
So do you want to tell everyone, did this work out? Were you able to be comparable to the simulations? What's the current status of this research?
I would say it's fairly in the early, fairly early on still, but I would say it's successful in the sense that we now know pretty well how to do this computation, and we are kind of at the stage where we can try to start exploring all the possibilities, right? So people have been exploring possibilities, different models in weakly coupled theories for quite some time, and people are getting increasingly good at it. But now we can also start to attempt to use holography to explore strongly coupled theories and see if, maybe we get the same, more or less the same qualitative results, or maybe we get some completely different things in general. And I think the main idea is to try to extract some kind of big picture, or how should I say, generic predictions, maybe. See what holographic theories tell you about these bubbles.
Yeah, I thought that was very exciting, very interesting to hear about, because I've always seen holography as something, it's a magic tool that some people use to go from string theory and gravity. It doesn't really apply to me. But now I'm working on bubbles, and you're coming along like, we can use holography to simplify your work. Okay, suddenly I'm very interested in holography. So it would be very cool to actually get to the point where we can be as good with holography as we are currently with the simulations, because always having two approaches to do things is just better in general, because then you can cross-check everything.
Right.
So it would definitely be good to get to the point where we can really use holography to study these things. I think it's very encouraging and very, very interesting to keep an eye on. So we are almost at 1 hour already.
Oh, yeah.
So
Nice.
is there anything about holography that you really want to talk about that we haven't had a chance to talk about yet, or anything you want to tell us about holography that you think the audience has to know?
Oh, that's a hard question. I think we touched on basically all the main things. I mean, I guess the thing that really kind of amazes me about it still is that, this is really connecting gravity and quantum gravity and string theory to something much that we thought, at least, we understood very well. I mean, these quantum field theories, again, they are complicated, they are hard to do calculations in, etc. But still, like, we have had them for quite some time. We kind of think we understand what they're about. Quantum gravity and string theory are sort of much more esoteric, weird things. But this holographic duality is really the realization that, if I write down a certain quantum field theory, like if I just write down the equation, then hidden inside there is string theory. Like it's just in there magically. And this is really amazing to me. It somehow blows my mind. So it's really like everything is connected, right?
It is really cool to think about it. We have a very nice question from Paul here of, which is the most exciting problem in physics that you think holography theory might help move forward? The most exciting, only one.
Let's see. I guess I should say what I'm currently working on, whatever I'm currently working on.
No, you can say anything.
I would probably say, I mean, okay, what I want to say is finite or non-zero density or high density quantum field theory in general. It's a very broad thing, but basically, roughly speaking, the problem is that when we want to describe materials or substances at very high density, things also get very hard in quantum field theory, and holography does this very easily. However, on the other hand, holographic duality does this very easily. So I think that's one thing. And to make it a bit more concrete, so that's a very vague answer, but a bit more concrete, I mean, this has applications to, for example, neutron stars, which is something that you might have or will talk about on this show.
We haven't done yet. We should.
Yeah, you should. That's a very fascinating topic. And actually many people here in Helsinki that work on it. And holography might be useful to describe the the phases that occur inside a neutron star, for example, which are at extremely high density. So okay, let's say that. I would like to say even more things, but maybe I should stop there.
Let's go with that. We have a very technical question from Jasmine, so let's give a brief answer to this one. Do you need a strongly coupled theory for a strong first-order phase transition?
No, you do not. For a strong, no, not even that. No, I actually don't know if there's a relationship. Maybe it's more likely somehow at strong interaction, but no, I don't. In general, you don't need that.
Yeah, no. I would say, to my knowledge, which is limited, but I would say, yeah, we don't need a strongly coupled theory for that. Yeah. Okay, so we have reached the 1 hour mark, and just one question that I love to wrap up with. Apart from holography, what field of physics, or in general of science, do you think is super fascinating? Like, what would you work on if not holography?
Yeah, so very hard question also, because I think many things are extremely interesting. Cosmology is one thing holographic duality has something to do with gravity, but like really proper cosmology, like you do, Diana, is something I recently became more and more fascinated about. So that's something I would not be unhappy at all to study. But also, honestly, like probably math, like pure math. If I hadn't gone into physics, probably that would have been the second choice. And then then the list could go on. But yeah, math is amazing. So that's probably the one thing.
Math is fun, but also scary and difficult sometimes. As David Dunn is pointing out here in the comments, the correct answer to that question is always going to be the cosmic microwave background radiation, because that's my favorite thing in the universe. But obviously, everyone's entitled to their own opinions, and not everyone will pick the CMB. But the CMB was the correct answer.
Well, it's a subset of cosmology, at least.
Exactly, so it's included in cosmology, so it counts. Yeah. Okay, so then this brings us to the end of the show. So thank you very much for joining. This, at least for me, has been very enlightening, and I hope you enjoyed being here on the show.
I did, yeah. It was very, very fun.
Yeah, and if you ever want to come back, you're always welcome back on Cup of Cosmology.
I think I would like to, yeah.
Awesome. So for everyone else, thank you for being here. Thank you, everyone, for all the great questions. We've had some really, really cool questions. As always, feel free to leave questions on the YouTube video afterwards. We might try to answer them. We might not, but feel free to leave comments on the YouTube video as well. And please do subscribe to the channel, click the like button, all the usual things. I should be online next Sunday. I still haven't figured out the topic for next Sunday. But as it's getting close to Pride, maybe we'll do something for Pride, but we'll see. I will be back online next Sunday, and then I'll be on a break. But next Sunday, back to my usual slot, so 15 minutes earlier than we started today. I hope to see you all next Sunday, and I hope in the meantime, everyone stays safe and takes care of themselves. And thank you once again, Oscar, for joining.
Yeah, thank you, Diana. And thanks, everyone.